Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good day to whom is my concern. Welcome to all of you to my video. My name is Idris Saad. I do hope that you and your family had a wonderful, happy and healthy day every day. May Allah bless us all in the best of iman and taqwa, inshallah. This video is made for my series of lecture on the subject of MEC451 thermodynamic. Please note that this video is best viewed with reference to the lecture note that I have provided earlier to all of my students. Also, please note that this subject is specifically designed for UITM student in the program of EM220 Bachelor of Engineering Honors Mechanical and EM221 Bachelor of Mechanical Engineering Manufacturing Honors. Even so, I do welcome anyone who would like to watch this video to learn something about the thermodynamic that inshallah could benefit your general knowledge. This is video for the lecture of chapter 2 properties of pure substance. Basically, this video is for chapter 2 part 1. In this chapter 2 part 1, I will cover two topics only, which are introduction to the pure substance and property diagram for phase change process. That is for this video chapter 2 part 1. Okay, now let us proceed to the content of this chapter. Okay, we start this chapter by looking at the outline of this whole chapter. Basically, there are four main topics only for this chapter. As you all can see on this slide, this chapter only consists of the pure substance, property diagram for phase change process, property table, and the final one is ideal gas equation of state. For your information, in this course, we will focus on three pure substances only. They are water, refrigerant 134A, and ideal gas. This is because the other substance will actually behave quite similar to these three substances, or we can make approximation to these three substances. For the pure substance, we will learn about the phase of the pure substance as well as the phase change processes of the pure substance. In the property diagram for the phase change process, we will identify the phases of the pure substance as it will exist in five possible phases, such as in the compressed liquid, saturated vapor, superheated vapor, as well as in the mixture phase between liquid and vapor. Furthermore, in the mixture phase, we will learn a new thermodynamic properties that is called quality of vapor and moisture content of the liquid. Those phases will be plotted in the TV diagram and the PV diagram of the property diagram. Based on the property diagram of the phase change process, we are required to determine the thermodynamic properties to do the analysis. Therefore, we will learn to read the property table that I have provided to you to find the properties of the water and refrigerant 134A. As for the ideal gas, the related thermodynamic properties can be obtained by calculation using the ideal gas equation of state, which is PV is equal to mRT. Hence, we will be learn about the ideal gas law for the substance of the ideal gas. So that's all about the outline of this chapter 2. Okay, now let us learn what is the meaning of the pure substance. The pure substance basically is defined as any substance that has a fixed chemical composition throughout. A pure substance does not have to be a single chemical element or compound. However, A mixture of various chemical element or compound also qualify as a pure substance as long as the mixture is homogeneous. What is meant here is, as long as the chemical composition of the substance will remain constant during any thermodynamic processes, it is considered as a pure substance. Let us consider a water as our substance. We all know that the chemical composition of the water is H2O. So, now let us consider that water in the solid phase, or we call it as an ice cube. The chemical composition of the ice cube is H2O. Then we leave it in the surrounding area and that ice cube will melt and changing its phase into water. Now, although the ice cube is changing its phase to water, the chemical composition of the water is still remain as H2O. Then, we may boil the water to become steam, or in thermodynamic language, we call it as vapor. Still, the chemical composition of the water is H2O. If we reverse the process from vapor to liquid to solid, the chemical composition of the water is still remain as H2O. No matter how many times we repeat this process, the chemical composition of the water is still H2O. So that, as a conclusion, if any substance can behave like water to retain its chemical composition, then it is considered as a pure substance. On contrast to the pure substance, let us consider the water that is mixed with the salt. Salt is actually a sodium chloride. If we boil the water that is mixed with the salt, then the taste of the water becomes too salty. That means during boiling process, part of the water is evaporated and leave the salt in the form of water in the pot. So the chemical composition of the water that is mixed with the salt is not a pure substance. Air is also considered as a pure substance, although it is a mixture of several gases. A mixture of liquid and water vapor is a pure substance, but a mixture of liquid and gaseous air is not. That is because the chemical composition of the water is H2O and the chemical composition of the air is include the nitrogen, carbon dioxide and other chemical composition. So, the clue is any mixture of chemical composition, as long as there is no change of its chemical composition, then it is considered as a pure substance. The figure on the right hand side of this slide shows the pure substance for the illustration purposes. Basically, as we all aware, the substances exist in different phases. For example, at room temperature and pressure, copper is solid and mercury is a liquid, even though they are both in metal families. Fundamentally, the phase of the substance is depend on a certain thermodynamic condition. That is because all of the substance exists in the real world are based on its molecule. Under different conditions, each substance may appear in different phases and each with different molecular structure. Please note that it is the same molecule, but the arrangement of the molecule is different. That's what is meant by different molecule structure. For any substance exists in this world, there are three principal phases, which are solid, liquid, and gas. For the solid phase, the molecule of the substance are arranged in three-dimensional pattern or we call it as lattice. It means that the molecule is arranged as a rigid structure of fixed position as illustrated in this figure. So as you can see on this figure, okay, you can see the molecule is arranged structurally. In the case of liquid phase, the molecule of the substance are not longer at a fixed position relative to each other, and they can rotate and translate freely as I showed in this figure. So this is figure illustrate how the molecular structure of the liquid. As you can see, the molecule can move from one position to the other position freely. However, they are still attached to each other. Finally, in the gas phase, the molecule of the substance are far apart from each other and a molecular order is non-existent. It moves about at random, continuously colliding with each other and the wall of the container they are in as shown in this figure. As you can see in this figure, okay, so the molecule can move freely inside the container. So they are not attached to each other. So as to this point, that is about the this is about the principle of the phases of the pure substance. Remind me again why we need to learn about these phases of the pure substance. That is because energy is invisible and it need to be existed in the substance. And we are study about transferring the energy from one position to another and from one form to another. So, as the substance change its phase, it will affect the energy. That's why we need to be learn the phase changes process. From previous slide, we just learned about three principal phases for a pure substance, which are solid, liquid, and gas. However, there are many practical situations where two phases of a pure substance coexist in equilibrium. For an example, water exists as a mixture of liquid and vapor in the boiler and the condenser of a steam power plant. Another example is the refrigerant change phase from liquid to vapor in the freezer of a refrigerator. Actually, the thermodynamic study is interested that the substance is exists in these two phases, which is liquid and vapor. The benefit of the substance exists in the liquid phase is it is easy for the storage and transportational purposes. As for the vapor phase, the benefit is the molecule will move faster to transfer the energy. As I explained earlier, the molecule in the vapor phase or in the gas phase are no longer attached to each other and they are freely to move around the container they are in. Because of that, this section is focused on the liquid and vapor phase and the mixture of these two phases. In general, all pure substances will exhibit the same general behavior. So, if we study the behavior of the water, so it will become a general idea for other substances as well. In order to understand the behavior of the phase change of the water, let us consider the process of boiling the water. Actually, we can boil the water in two ways. The first one is we can increase the temperature of the water by giving the heat to the water in the atmospheric pressure. This is the normal process that we normally do. This process thermodynamically called as increased temperature at a constant pressure. The second way is if we have a water that have been compressed at very high pressure, we can reduce the pressure of the water, but we can maintain the temperature. This process is known as decreased pressure at constant temperature process. Okay, let us discover how water behaves when we change its phase through these two processes. Okay, this is experiment number 1 to demonstrate to you how the water will behave when we change its phase from liquid to vapor by increasing the temperature of the water but maintain the pressure of the water. Okay, at the first, let us consider a water in the frictionless piston cylinder device as shown on this slide. Frictionless piston mean the piston can freely move whenever higher pressure develop more than 1 atmospheric pressure or higher than the weight of the piston. As we all can see on that figure, the properties of the water are 1 atmospheric pressure. So this is basically due to the atmospheric pressure that pushing the piston, and also the temperature is 20 degrees Celsius. So we can name it as state 1. At 1 atmospheric pressure and 20 degrees Celsius, normally the water is existing in the liquid phase. In thermodynamic language, we call it as compressed liquid. Why we call it as compressed liquid? It is because the water in the liquid form is compressed by atmospheric pressure. Anyhow, all of the substances in this world is basically compressed by the atmospheric pressure. Okay, that is about the name of the compressed liquid. From that, we can plot the property diagram. For this process, we normally use the temperature in the y-axis. For the x-axis, we may use the volume or the specific volume. It does not really matter. Why it does not really matter? The answer is the piston cylinder device is the closed system. Hence, the mass is constant throughout the process. Then, if the volume is increased, so does the specific volume. Anyways, the specific volume is calculated by the volume over the mass. So, it does really matter whenever we use the volume in meter cube or the specific volume in meter cube per kilogram. However, the most popular properties for the x-axis is the specific volume. Because of that, this property diagram is named as TV diagram. So, based on the temperature and pressure we are currently have, then we can plot the state 1 in the TV diagram as this. Now, we have state 1 in the TV diagram. Next, we heat up the water by putting the fire under the cylinder like this. Okay, now when we wait for some time, the water will be boiled. This is recorded as state number 2. At this state, all of the water is still in the form of liquid. When we check the properties of the water, the temperature has increased to 100 degrees Celsius, but the pressure is remain unchanged at 1 atmospheric pressure. Also, the volume of the cylinder is also increased a little bit. What is mean here is when the water is boiled, its molecule will expand a little bit and generate the pressure higher than the atmospheric pressure. That pressure will push piston away since the piston is free to move or frictionless until both pressure reach an equilibrium pressure. That means the pressure of the water inside the piston cylinder device have equivalent pressure to the atmospheric pressure. That's why the volume of the cylinder is increased. So now we can plot state 2 in our TV diagram. As the heat is continuously transferred into the water, we can see that part of the water has changing its phase into the steam, or we call it as vapor, and part of it is still in the liquid phase. Let's say this as a state 3. When we check the properties of the water, we will find that the temperature is still 100 degrees Celsius and the temperature is also remain unchanged at 1 atmospheric pressure. This value of pressure and temperature are similar to state number 3. However, the volume of the cylinder is way increased to occupy the steam or vapor that has been developed. Now we can plot state 3. Okay, as we continuously observe this experiment, we will find that at one position, all of the water will change its phase to a vapor. This is recorded as state number 4. Okay, at this state, again, the pressure and temperature are remain unchanged as state number 2 and state number 3. But the volume is way higher than state number 3. We are now can plot the state number 4 in the TV diagram. What we will find on this TV diagram is starting from state number 2 where the water is start to boil until all of the water is changing its phase from liquid to steam, or we call it as vapor. The pressure and temperature are remain unchanged, or it is constant. The only properties that is changing is the volume of the cylinder. So that in conclusion, the water is changing its phase during constant pressure and temperature processes. So you have to remember that one. So the water is changing only when the pressure and temperature are constant. Next, when we keep going heating up the vapor, and we can record this as state number 5, we will find that the pressure is remain constant, but the temperature is increased drastically. For sure, the volume is also increased. Now we can plot state number 5 in our TV diagram. Okay, let's stop the experiment for now. Referring to the TV diagram in this slide, we are now having 5 states on that property diagram. What we are going to do now is we connect the state from state number 1 to state number 5. At first, we connect between state 1 and state 2. Please remember that at this condition, all of the water is still in the compressed liquid form. Then we will connect the phase change process from liquid to steam or vapor, which are from state 2 to state 4. Finally, we can connect the phase of water in the steam or a vapor phase from state 4 to state 5. Basically, this is the behavior of the water when we change its phase from liquid to vapor in the constant pressure process. Note that the key point here is the water is changing its phase at constant pressure and temperature. In the previous experiment, we boiled the water at 1 atmospheric pressure. Basically, we can repeat that process with different pressure again and again. When we repeat that experiment with various pressures, we are actually will have relatively similar trend of the phase change process up to a certain point or up to a certain temperature limit. Then we can plot all of the behavior of the water in one TV diagram as shown on this figure on this slide. As you can see on this slide, the different pressure of different experimental is linearly increased starting from 0.01 MPa up to 25 MPa. For this TV diagram, we are actually have three important characteristics of the water for the phase change process. Number one, water will start to boil at much higher temperature when we perform the experiment at higher pressure. In simple words, the higher the pressure of the water, the higher the temperature it will boil. Number two, the specific volume of the point between compressed liquid and mixture is increased as the pressure of the water is increased. What is mean here is, if we perform the experiment with higher pressure, state number 2 is also higher. Okay, number 3, the specific volume of the point between mixture and vapor is decreases as the pressure is increased. In another word, state number 4 is inversely proportional to the experimental pressure. The higher the experimental pressure, the lower state number 4. That are the three important characteristics of the phase change process of the water. If we look at the TV diagram closely, as the experimental pressure is further increased, this saturation line or the line in the mixture region or the state 2 and state 4 will continuously to get shorter and shorter, and it will become an intersection point when the pressure reach 22.06 megapascal. This point is called as the critical point, where it is the point at which the saturated liquid and saturated vapor state are identical. The temperature, pressure, and specific volume of a substance at the critical point are called respectively the critical temperature, critical pressure, and critical specific volume. When the pressure goes above the critical pressure, there will not be a distinct phase change process as figure aside. Above the critical state, there is no line that separates the compressed liquid region and the superheated vapor region. What is mean here is, we could not identify the mixture region since the substance will change its phase very quickly from liquid to vapor. It is customary to refer to the substance as superheated vapor at temperature above the critical temperature and as compressed liquid at temperature below the critical temperature. In this slide, I will explain to you the detail about the TV diagram. Basically, we can connect all state 2 and state 4 as shown here to become a line as shown on this TV diagram. As you can see on this slide, this is actually the typical TV diagram for the phase change process. Now, let us get to know the item in this TV diagram one by one. The first one is the compressed liquid region. As you can see on this TV diagram, it is the region that nearest to the y-axis of the temperature. Fundamentally, the compressed liquid region is the region where all of the substance is existing in the liquid phase. In another word, it is the region where a substance that is not about to vaporize. As we all know that the vaporization process is where the water will start to change its phase from liquid to vapor or gas. So, as a summary, the compressed liquid region is where the substance is existing in liquid phase and not about to vaporize. The next item that we should understand in this TV diagram is the term saturation. It is actually a terminology to describe a condition in which a mixture of vapor and liquid can exist together at a given temperature and pressure. Actually, when we heat up the water will absorb the heat and contain the heat within its molecules. That's why the water become hot from 20 degrees Celsius to 100 degrees Celsius as we discussed in the process of boiling water in slide number 6 previously. However, after 100 degrees Celsius, the water could not contain the heat energy anymore. That is the limit for a water to contain heat energy at 1 atmospheric pressure. As we continuously giving heat to the water, the molecule of the water are using that heat energy to change its phase from liquid to vapor. That's what is meant by the saturation, where the water could not contain the heat energy anymore and start using the extra heat energy to change its phase from liquid to the vapor or gas phase. That's why the saturation is defined as a condition in which a mixture of vapor and liquid can exist together at a given temperature and pressure. Based on this statement, we need two intensive properties of the pressure and temperature to define the term saturation. Since we perform the experiment in constant pressure process, then we should learn about the saturation temperature. The saturation temperature, which is denoted as T sat as shown here, is defined as the temperature at which a pure substance changes its phase at a given pressure. As you all can see on this diagram, the pressure line, which is plotted in a dashed line on this TV diagram, the P2 is higher than P1. Therefore, the saturation temperature between P2 and P1 are different. So, that is meant by the saturation temperature. The next item in this TV diagram is the saturated liquid vapor mixture region. It is the region or a state at which the liquid and vapor phases coexist in equilibrium. Recall back the process of boiling the water. At 100 degrees Celsius, the water starts to boil, and part of the water is changing its phase from liquid to steam, or we can call it as vapor or gas. This condition will continuously occur until all of the water changing its phase from liquid to vapor. This is the region that we call it as saturated vapor region. We also call this region as a mixture region since part of it is the water in the liquid phase and part of it is the water in the vapor phase. So, the boundary between the compressed liquid region and mixture region is known as the saturated liquid. So, in order to differentiate these two regions properly, we normally draw the line as shown on this TV diagram, and it is known as saturated liquid line. The saturated liquid is defined as a liquid that is about to vaporize. It is actually state 2 in slide number 6. Thus, this will make the saturated liquid line as the boundary between the liquid and mixture phase. Next, as we continuously giving heat to the water, all of the liquid is changing its phase to vapor. So that this is known as the superheated region. By definition, this region is a region where a vapor is not about to condense. Well, condensation means a process of changing the phase from vapor to liquid, as what happened to our cloud and rain as we study the basic science in the high school. So, what is mean here is the vapor have high heat energy and it will not condense at this region. So now we need to have a boundary between the mixture region and the superheated region. That boundary is called as the saturated vapor, and also we can make a line that is called as saturated vapor line. At this boundary, scientifically, it is defined as a vapor that is about to condense. However, it's just an imaginary boundary that is used to separate the mixture and superheated region. So, that's all the important item that you all need to memorize and understand. In actual thermodynamic analysis, this TV diagram is very important. Hence, I wish you a very good luck to understand all of this phase change process of the pure substance, particularly this TV diagram. In the previous slide, I have mentioned that we need two intensive properties in order to define the boiling state of the water. Basically, this is according to the state postulate. That two intensive properties are the pressure and temperature. The temperature at which water start boiling is actually depend on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. Table 3.1 in this slide is presenting the saturation pressure of water at various temperature. As we all can refer to that table, as the temperature is increased, so the saturation pressure. For an example, if we want the water to be boiled at negative 10 degrees Celsius, then we are required to set the experimental pressure at 0.260 kilopascal. If we look at the table closely, we can see the pattern of the relationship between pressure and temperature for the boiling process. They are actually proportional to each other. Based on that table, the scientists also plot the property diagram of the pressure in the unit of kPa and temperature in the unit of degree Celsius as shown here. As you can see on this PT diagram, the curve is almost parabolic. Based on this PT diagram, we can easily know the boiling temperature for the water for any given pressure, also vice versa. That is the relationship between the pressure and temperature for the boiling process. Table 3.2 illustrates the variation of the standard atmospheric pressure and the boiling temperature of water with different altitude. So, you may use this table to boil the water if you are climbing the mountain or digging your own graveyard or whatsoever. Basically, this is the relationship between pressure and temperature for the boiling state of water. Okay, now we need to define the state of a substance based on the phase change process on the TV diagram. The main idea behind this definition is to know the phase of the substance for a particular state. Recall that in order to define the state, we only need two independent intensive properties. That is based on the state postulate. So, for our TV diagram, we are actually have three properties. One is temperature, the second one is the specific volume, and the third one is the pressure. So, in order to define the state, we just need the intersection between these two intensive properties only. What is mean here is, if we know the value of the pressure and temperature, then we can plot the state on this TV diagram. Based on that, we can easily identify the phase of the substance as well as get the value of the specific volume based on this TV diagram. Similarly, if we know the value of the specific volume and pressure, we also can plot the state on this TV diagram. So, we can identify the phase of the state and also get the value of the temperature. So the process can be repeated with the other two intensive properties. Next, the other important state that we need to learn is the saturated liquid and saturated vapor. Basically, for the x-axis in the property diagram, we can also be used as a specific enthalpy, H, specific entropy, S, and specific internal energy. As you can see in this property for the x-axis, they are subscription of F and G. Subscript F mean that particular property is belong to saturated liquid, while subscript G mean that particular property is belong to the saturated vapor line. For an example, if we have V subscript F, that means the specific volume at saturated liquid line. Also, if we have H subscript G, then that enthalpy is on the saturated vapor line. Moreover, we will have the property such as U subscript Fg. This is actually mean the internal energy at the superheated vapor minus internal energy at the saturated liquid line. Or in another word, the enthalpy of saturated vapor minus the enthalpy of saturated liquid. So that is the other information regarding to the TV diagram. Going back to our main subject of defining the state of the substance, if the temperature of the liquid is lower than the saturation temperature for the existing pressure, or we can write it as T is smaller than T sat at P1, then the state is in the compressed liquid region. If we have a substance that is exists as a liquid at the saturation temperature and pressure, or we write it as V is equal to Vf at T sat, then it is a saturated liquid. For the saturated liquid vapor mixture, the state must lie at which the liquid and vapor phases coexist in equilibrium, or we may write as Vf is smaller than V is smaller than Vg at T saturation. For the saturated vapor, the state of the substance exists entirely as a vapor at saturation temperature, or we can write it as V is equal to Vg at T saturation. Finally, for the superheated vapor, when the vapor it is at a temperature which is greater than saturation temperature, or T is smaller than T saturation at P1. Okay, so that is how we are defining the state of a substance in the TV diagram. Okay, now we move on to the second experiment of phase change process, which is decreased pressure at constant temperature. In the previous experiment, we boiled the water at constant temperature, but we increased the temperature of the water. Now, we will boil the water at constant temperature by reducing the pressure of the water. Let us consider a piston cylinder device that contains a liquid water at 1 megapascal and 150 degrees Celsius as shown here. Water at this state exists as a compressed liquid. Now, let us reduce the pressure on top of the piston gradually or little by little. When we reduce the pressure on top of the piston gradually, the water is allowed to exchange heat with the surrounding. When the heat in the water is exchanged with the surrounding, then its temperature will remain constant. As the pressure decreases, the volume of the water will increase slightly. When the pressure reaches the saturation pressure value at specified temperature at the pressure of 0.4762 megapascal, the water will start to boil. During this vaporization process, both the temperature and the pressure will remain constant, but the specific volume would be increased. Once the last drop of liquid is vaporized, further reduction in the pressure results in a further increase in specific volume. Based on this process, we can plot a property diagram of the PV diagram like this. If you look at this PV diagram, the compressed liquid region, mixture region, as well as superheated region are very similar to the one of TV diagram that we have discussed earlier. However, the line of constant temperature is moving from top to the bottom of the PV diagram, unlike the line of constant pressure in the TV diagram that is moving from bottom to the top of the figure. Also, since this process is a constant temperature process, then we have a saturation pressure rather than saturation temperature on this PV diagram. The saturation pressure is defined as the pressure at which a pure substance change phase at a given temperature. After we have the PV diagram, we then need to define the state of a substance in this PV diagram. Actually, the way to define the state of the substance in this PV diagram is very similar to the way we define the state in the TV diagram. Let's say we have the state here or in this position. Then these states are in the compressed liquid region. If we have the state here or the state in here, then those states are in the mixture region. Furthermore, if we have the state in this region like this or like this, so those states are in the superheated region. Also, if we have the state in here or here, then those states are on the saturated liquid. Finally, if the states are in here or here, then it is on saturated vapor. That is how we define the state of a substance in the phase of in the PV diagram. Similarly, so basically the other information is exactly similar to the PV diagram. So this is how we define the state in PV diagram. In those two experiments that we have discussed earlier, we only consider changing the phase of the water in the liquid to the gas phase or the other way around. Actually, we can extend the diagram to include the solid phase for the water, or in another case, or in another word, we can include what we call the ice cube in our experiment. As you all can see on this slide, when we include the solid phase, then we will have what we call a triple point. A triple point is the temperature and pressure at which a substance can exist in equilibrium in the solid, liquid, and gaseous phase. The triple point of the pure water is at 0.01 degrees Celsius and 273.16 Kelvin of mercury. The major use of the triple point of water is to calibrate our thermometer. However, for our course, we limit the study up to liquid and vapor phase only. So you don't need to worry about the solid phase. When we want to include the solid phase in the phase changing process, for a certain substance such as firewood, it will change directly from solid to gas without passing through the liquid phase. This is called as sublimation. The sublimation is occurring at the pressure and temperature below a substance triple point in its own phase diagram, which is correspond to the lowest pressure at which the substance can exist as a liquid. The reverse process of sublimation is deposition or desublimation, in which a substance passes directly from a gas to a solid phase. Sublimation has also been used as a generic term to describe a solid to gas transition followed by a gas to solid transition, which is deposition. While a transition from liquid to gas is described as evaporation if it occurs below the boiling point of the liquid, and as boiling if it occurs at the boiling point, there is no such distinction within the solid to gas transition, which is always described as sublimation. The pressure and temperature diagram that include the sublimation, vaporization, and melting is presented in this slide for your reference to differentiate the solid phase, the liquid phase, and also the vapor phase. For extending the phase change diagram to include the solid phase, we are also can plot it by using three-dimension axis. As you can see on this figure, it is a pressure, volume, and temperature property diagram in three dimensions of the surface of a substance that contract on the freezing. Based on this diagram, we can easily identify the solid, liquid, vapor until gas phase of the phase change process that related to the pressure, volume, and temperature. Also, on this figure, will present the pressure, volume, and temperature property diagram in 3D. but it is plotted the surface of the substance that expand on the freezing. Similarly, we can see on this property diagram the relationship of the phase change process to the pressure, volume and temperature. The PVT surface properties diagram present a great deal of information at once. So what is mean here is at one diagram we can see the value of pressure, volume and temperature for all what we call phases for the phase changes process. But in a thermodynamic analysis, it is more convenient to work with only two-dimension diagram rather than three-dimension property diagram such as PV and TV diagram. So as a conclusion for our course, we will only deal with 2D property diagram only. So that's all about the phase change process of a pure substance. Okay, now we will move on to the next topic, which is the latent heat. By definition, the latent heat is the amount of energy that being absorbed or released during a phase change process, or the specific enthalpy difference between two phases of a substance at the given temperature and pressure. In order to understand this, we need to refer back to our property diagram, whether TV diagram or PV diagram. As you all can see on this TV diagram for an example, during phase change process from saturated liquid to saturated vapor, the pressure and temperature are both constant. But at this time, we are actually continuously giving the heat energy to that particular water. What happened here is actually the heat energy that we gave to the water is used to change its phase from liquid to vapor. So, in another word, the amount of energy that used by substance to change its phase is the enthalpy. That means since the phase of the water start to change from saturated liquid to saturated vapor, then the amount of energy at this duration is called the latent heat. Actually, we use the enthalpy to calculate the latent heat. This is because a phase change is generally accompanied by a volume change and therefore involve PV work as well. No worries for now. I will explain to you about the enthalpy in the next slide. Recall that any pure substance, like water as an example, can change its phase in both directions. We can change the phase from solid to liquid to gas. Also, we can change the phase of the water from gas to liquid and also to solid. Because of that, we have two types of latent heat. One is fusion and the other one is vaporization. Latent heat of fusion is actually the amount of energy that is being absorbed during a melting process. It is also equivalent to the amount of energy that is being released during a freezing process. So, the latent heat of fusion is the energy that is required to change the phase of the substance between solid and liquid phase, whether from solid to liquid or from liquid to solid phase. As for the latent heat of vaporization, it is actually the amount of energy that being absorbed during vaporization, and it is also equivalent to the energy that being released during condensation process. That means the latent heat of vaporization is the energy that is used to change the phase between liquid and vapor in both directions for the pure water. The magnitude or the value of the latent heat actually depend on the temperature or pressure at which the phase change occur. As we refer to the TV diagram in this slide, the higher the experimental pressure, then saturation temperature is also higher. But at the same time, the latent heat become fewer. As an example, at 1 atmospheric pressure, the latent heat of fusion of water is 333.7 kilojoule per kilogram of water, and the latent heat of vaporization is 2256.5 kilojoule for 1 kilogram of water. That is because the difference between molecule arrangement of the solid and water is relatively close enough, as we see on the microstructure, or we can see what we call the molecular arrangement of the solid and liquid. But the different molecule arrangement between liquid and gas is relatively large, since for the gas it can move freely without any hesitation within its container. That's why the value of the latent heat of vaporization is much higher than the latent heat of fusion. Okay, in this slide, as I told you previously, I will explain the meaning of the enthalpy. In order to understand the meaning of the enthalpy, we need to consider the figure on an open system like this. As we know, in the open system, internal energy, pressure, and also specific volume can flow in and out of the system. Basically, enthalpy is a measurement of energy in a working fluid or a substance of a thermodynamic system. It is actually equal to the sum of the internal energy of a body or a system and the pressure multiplied by the product of its volume. Mathematically, it is written as H is equal to U plus P times V in the unit of kilojoule. We also can write the enthalpy per unit mass as written here in the unit of kilojoule per kilogram. Now, the unit of enthalpy is per kilogram. Recall back the topic of property of a system in a video chapter 1 part 2. This is actually the specific properties. It is actually called the specific enthalpy. Since our course on the study between liquid and vapor, then we can define the enthalpy of vaporization as per T or PV diagram like here. Referring back to the topic of defining the state of the pure substance, subscript F is identified as saturated liquid. Subscript G is marked as saturated vapor, and subscript Fg is the difference between vapor and liquid. Then, the enthalpy of vaporization is actually Hfg. It is the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. Because of that, the total amount of the latent heat of the process is the difference of the enthalpy, or mathematically we can write it as delta H. So there is mean by the enthalpy and its relationship between the phase change process. Actually, we have finished the video of chapter 2 part 1. Alhamdulillah. Thank to Allah. Recall that In this video, I have explained to you about the pure substance that include the phase and phase change processes of a pure substance. Also, I have explained about the property diagram for the phase change process. We learned about the compressed liquid, saturated vapor, superheated vapor, the TV diagram, and finally, we have learned about the PV diagram. If you have any question regarding to this video, please ask it in our WhatsApp group or in our video conference later. Hopefully, this video will benefit your knowledge about the thermodynamic and inshallah you can score in this subject. So the last word from me is I will say that the good thing of this video is come from Allah subhanahu wa ta'ala, and the bad thing of this video is coming from my own weaknesses. With that, thank you very much and good luck in your study and in your life. Wassalamualaikum.